I'm your guide for today, a science communicator who fell in love with fossils the first time a museum guard let me touch a slab of limestone and said, quietly, that the ripples on its surface were waves from a beach 100 million years gone. Hold that feeling with me as we step into the world of pterosaurs, the original masters of real-powered flight long before birds. Picture a coastline at dusk in the late Jurassic. The sea is pink glass, cliffs smell of salt and resin, and the sky is busy with silhouettes that look like kites come alive. They are not birds and not bats, they are archosaurs, close cousins of dinosaurs, and they solve the problem of flight in their own way. With a wing stretched from a super elongated fourth finger to the ankle, a living sail supported by layers of internal fibers. Their time spans roughly 230 to 66 million years ago, from the late Triassic to the very end of the Cretaceous, and across that arc they range from bad-sized hunters as nimble as swallows to giraffe-tall giants that could look a giraffe in the eye. When we first meet them in the Triassic, forms like Eudimorphodon already show flight-ready bodies, thin-walled, pneumatized bones, a keeled breastbone for strong flight muscles, and a special wrist bone, the pteroid, that supported a forward membrane, acting like a controllable leading-edge flap. The membranes themselves were not simple sheets. In many fossils, especially under special lasers and UV light, we can see actinofibrils, microscopic reinforcement strands that stiffen the wing, allowing camber control like a built-in aircraft wing. Some specimens even preserve fuzzy coverings called pycnofibers, hair-like filaments that trapped heat, suggesting warm-blooded metabolisms. If you have ever wondered whether deep time felt cold and alien, the fuzz on a pterosaur says otherwise. Warm blood beats in the dark, even for a reptile. A lesson emerges early. Nature will reinvent a good idea in different bodies, and flight is so useful that life tried it at least 3 times with birds, bats, and pterosaurs. The pterosaur solution is uniquely elegant. Instead of launching like birds with a hop and wing beat from the hind legs, they likely vaulted into the air with the front limbs, a quadrupedal catapult. Think of a pole vaulter who carries their own pole. In the bones of the forelimb, powerful flexors snap the body upward, wings already open, the ground gone in a heartbeat. Trackways from ancient mudflats record them as for footed walkers on land, hands rotated outward, leaving prints with little 3-jointed fingers beside a deep pit where the long wing finger did not press. On the wing, they were artists of the wind. Crests rose from many skulls like sails or helms, tall, thin, sometimes tooth-combed, sometimes smooth as a blade. These weren't just ornaments. In some species, they likely helped with display and balance, and in others they may have acted like control surfaces. Pteranodon from the western interior seaway carried a backward sweeping crest and a toothless beak like a spear for fish, while Ramphorhynchus from Solnhofen limestones had a long tail ending in a diamond vein and needle teeth that interlocked into a fish trap. Tapeyards bore extravagant headgear and beaks shaped for fruit, hinting at inland forests and the first aerial gardeners spreading seeds above river plains. Pterodostro sifted shrimp and plankton with hundreds of fine comb-like teeth, turning moonlit lagoons into feeding grounds with each patient sweep. Istiodactylus carried shovel-shaped teeth made for slicing, a scavenger in the open sky. And in the late Cretaceous, Osdarchids, such as Quetzalcoatlus, grew colossal, with wings nearly as wide as a small airplane. For years we argued whether such giants could truly fly. Bone strength calculations, hollow architecture, and the quadrupedal launch model suggest they could, at least for powerful takeoffs and long glides, though they also spent much time stalking on land like towering cranes, spearing small animals on flood plains. To meet a pterosaur is to meet a machine built for lightness. Skulls stretch into delicate beams. Backbones are fused into strong plates near the shoulders. The torso is short, the chest deep, the lungs likely bird-like with air sacs that moved air in a one-way flow, trading oxygen efficiently. Inside their heads, endocasts of the brain show enlarged regions that coordinate complex flight, especially the flocculus that integrates balance and eye movements. Scleral rings around the eye reveal day or night habits. Some species were probably nocturnal hunters of insects over warm water, while others chased fish in bright morning light. Not every fossil is a dramatic skeleton on a slab. One of my favorite moments in the field came with a small imprint from China, a parchment-like egg, soft-shelled, not the rigid calcite we know from many dinosaurs. Inside, the outline of a folded wing and a jaw of tiny teeth told a quiet story. Pterosaurs likely laid soft eggs in sand or soil, and the hatchlings, already winged, may have been capable of early, even immediate flapping flight. That image stays with me, a little life unfolding like a paper lantern, ready to catch the first breeze. Our wildlife artist for this episode, Lena, once told me that drawing the wing is like drawing a living parachute. She spent a week sketching under laser-stimulated fluorescence photographs that reveal fibers in Solnhofen wings. What looked simple at first became a marvel of architecture. Layers, tendons, a trailing edge that could tighten, or billow, a leading membrane that behaved like high-lift devices on modern aircraft. Her lesson, and mine, is that soft tissues change the story? For decades we imagined pterosaurs with limp, floppy sails. Now, with new imaging and glorious fossils from China and Brazil, we can see their wings were engineered by evolution for fine control, with texture and tension and warmth. To understand how these animals lived, follow me to a ridge of gray stone in Texas where the Big Bend sun feels like an anvil on your back. A fossil hunter on our team, Diego, wipes dust from a pale slab and a pattern emerges, honeycomb bone thin as a potato chip, a joint like a pulley, and a ridge where a wing membrane once anchored. This is the country of Quetzalcoatlus, the Late Cretaceous giant. In camp that night, Diego admits he doubted any creature that size could truly launch. Our biomechanics specialist shows him models that combine bone strength with muscle reconstructions and air density. The numbers say yes. With a vault from the forelimbs and a few heavy downstrokes, they could clear the scrub and ride thermals. And on calm days, they could walk miles, scanning for prey like a patient heron on stilts. The lesson writes itself in the wind around the tent. Nature often solves problems by combining parts we already understand. A pterosaur, a partnership between a catapult and a sailplane. The catapult is the launch, the sailplane is the glide. In coastal settings, long-winged forms likely soared on sea breezes much like albatrosses, banking along cliff faces and skimming lift from waves without touching the water. Inland, shorter wings and stronger limbs favored burst power and agile walking between flights. Skeletons tell us about structure, but color and behavior live in softer traces. Under microscopes, melanosomes from preserved filaments match shapes associated with browns and rusts in modern birds, suggesting patterns and shading that broke up outlines or flashed for display. Crests exaggerate those signals. Imagine twilight on a floodplain when a head banner catches low sun, orange like a slice of fruit. These are stories supported by measurements, not just wishes. When we compare crest sizes to body mass, we often see scaling that suggests sexual display, but we also consider aerodynamics because a surface exposed to the wind must obey the air. Science means asking whether an idea survives contact with physics. For years, many of us imagined skim feeding, where an animal flies with the lower jaw slicing water like a knife, but experiments show the drag would have been punishing for most pterosaurs. So, we adjust the picture. Dipping, surface grabbing, plunge snatching, and land stalking each fit certain skulls and wings better. Pteranodon likely patrolled the seaway for fish, but did not drag its beak constantly. As darchids hunted on land, Pterosaur filtered shallows like a living comb. Rhamphorhynchus left stomach stones and fish scales in slabs, as proof of nightly fishing trips. Tapejarids with short faces and big attachments for jaw muscles make sense as fruit pluckers in sunlit groves. What about growth and family life? Bone histology sliced paper thin reveals fast deposition and dense blood vessel networks, the signature of quick growth and high metabolism. Youngsters preserved in China show proportionally big eyes and fully formed wings, consistent with early independence, though adults may have guarded nesting areas the way modern seabirds do. Eggs with soft, leathery shells hint at buried clutches in warm ground rather than exposed nests, a strategy that protects moisture and temperature. In storms, whole colonies might have been vulnerable, and that may be why we sometimes find many individuals preserved together. In fine volcanic ash, another voice joins our campfire, a community storyteller named Mara who grew up near chalk cliffs. She remembers flying box kites over the beach and feeling how a small pull at the string can change everything. That is how she imagines a pterosaur managing its wing. A pinch here or a tension their changing camber and lift without flapping hard. I hand her a replica of a pteroid bone, that stubby wrist element that supported the leading membrane. She rolls it in her palm and grins. Small parts can control a sky. In labs far from deserts, engineers build robotic wings patterned on pterosaur membranes. They test how fibers resist flutter and how a living wing might shift stiffness from root to tip. Wind tunnels give us curves of lift and drag. Computer fluid dynamics lets us model gusts and stalls. Every plot forces our art to match math, and our drawings get better. If birds are feathered arrows and bats are fingertips riding in air, pterosaurs are flying sails with built-in spars, and that metaphor guides both illustration and reconstruction. Now widen the canvas to their world. Triassic survivors took to the skies above conifer forests and warm beaches. By the Jurassic they were diverse, long-tailed forms with vein tips, short-tailed forms with great wings, toothed and toothless, lagoon specialists and cliff riders. In the Cretaceous, ecosystems exploded, with flowering plants and new coastlines, and pterosaurs kept pace with a parade of crests and niches. But birds also rose, filling small flyer roles, and in many places pterosaurs shifted upward into larger sizes. Some think birds outcompeted small pterosaurs. Others think environmental change favored bigger wings. Whatever the balance, sky space is a resource partitioned by size and skill. That is why a city hosts swallows, gulls, hawks, and herons without chaos. Each has its way. So, too in the Mesozoic sky, where night, dawn, coast, and inland each offered a different runway, we return to fossils to ground the poetry. Scleral rings let us estimate pupil sizes and day habits. Bite marks on fish bones match tooth patterns. Isotopes in enamel whisper whether water was coastal or fresh water. Trackways in Morocco show quadrupedal walking with regular stride. Tracks in Korea preserve wingtips dragging for a moment during landing. Every line of evidence narrows the possible and leaves a core of confidence. The most important habit we keep, as scientists and storytellers, is to let new data revise our inner movies. It is tempting to hold onto a dramatic idea, but the real drama is change. When a laser reveals a previously invisible fiber network, we redraw the wing. When a computer model says a crest would torque the neck in a turn, we shrink or reshape it. Humility keeps us aloft. Dawn on the last day of the Cretaceous would have looked ordinary. Thermals rose over river deltas, as darchids paced among ferns. Small-toothed species hawked insects above quiet ponds. Far away a rock approached from space, and within hours the world changed. In the aftermath of the impact, fires and darkness and acid rain collapsed food webs. Most large animals perished, and pterosaurs, already tending toward bigger sizes in many places, disappeared entirely. Birds survived, perhaps buffered by diets that could pivot to seeds and hardy plants, by flexible reproduction, and by luck written into geography and habits. When the skies cleared, flight continued, but the original architects were gone. That truth used to make me sad in a way I could not explain. Then one field season, on a cliff above a chalky river in Eastern Europe, our rope team found a jaw piece of Hatzegopteryx, a gent with a skull like a bridge girder. We mapped the layers, photographed every fragment, and as the light turned gold the valley wind made the rope hum like a cello string. Extinction, I realized, is not just an ending, it is the price of a history long enough to include everything. The wonder is that we can read even a few pages. We read with CT scans that show hidden canals in bones, with synchrotron light that pulls chemical ghosts from sediments, with drones that photograph footprints from shadow angles, with artists who test anatomy by posing bodies in motion before a skeptical audience of wind and gravity. We read with collaboration, because no one mind can carry a sky full of data. A pilot and a paleontologist both know the feeling of lift at the edge of a stall. A sculptor knows when a wing root looks wrong because the balance of the pose fails. An ecologist hears a story in the spacing of nesting sites. When we put those languages together, extinct animals become less like puzzles, and more like neighbors we are slowly remembering. What did pterosaurs teach the world they left behind? They taught that biological flight has many solutions, that membranes can be as subtle as feathers, that insulation and high metabolism evolved in reptiles, that headgear can shout across a river without a sound, that soft tissues steer hard bones, that science is a moving target and the thrill is chasing it. They showed that giant size is not a myth if you solve takeoff first, and that walking well on land can live alongside mastery of the air. They seeded forests with fruit guts and carried genes across straits and mapped invisible highways of rising heat. And by vanishing, they cleared ecological space for a different course of flyers to grow loud. Back home, in a workshop that smells of plaster and coffee, Lena finishes a life-size wing section mounted on a hinge. She invites a class of students to grip the leading edge and feel how small changes in tension change everything. One student asks whether any modern animal flies with exactly the same plane. No, I say, and that uniqueness is part of their magic. Birds own feathers, bats own fingers, pterosaurs own the wind with a living sail. We walk to the parking lot, and the afternoon heat shimmers above the asphalt. You can see thermals by watching gulls circle, by feeling the way a kite tugs your hand, by tracking clouds that bloom and vanish. The air is not empty, it is structure and opportunity. Once you learn that, you start to notice the same truth in other places. A problem that seemed like a wall might actually be a gust waiting for a wing. A plane that looks fragile might hold because its fibers run the right way. A community can lift together when one person leans into their strongest direction. If you need a lesson to carry from the fossil cliffs, carry this. Elegance is not the same as fragility, and lightness is not weakness. It is an achievement, tuned and retuned by selection until it becomes strong in the exact way it needs to be. Pterosaurs embodied that principle. They were light precisely where lightness saves energy and heavy precisely where strength prevents failure. They committed to a plan and then evolved every small reinforcement that plan required. When we talk about climate change, or conservation, or engineering, or art, we can borrow that mindset and ask, where should we be light? Where should we be strong? And how do we adjust tension so we can ride the next thermal together? I think of Diego on the ridge and Mara by the sea and Lena in the studio, and the many patient preparators whose names do not make the papers. We stand on a long chain of hands and minds. The animals we study stood on lines we cannot see anymore, but the physics is the same and the stories are written in stone. Tonight, if the sky is clear, look for the moon, then for the dim river of the Milky Way. Imagine outlines of wings between the stars, a memory of sails that once turned sunlight and warm air into life. No human will ever watch a living pterosaur launch into a crimson sunrise, but we can get close by staying honest with evidence and generous with imagination. That is the pact we make with the deep past. We promise to do the work carefully and to keep the wonder alive. And in return, the fossils keep giving us gifts, a fiber in a wing, a ring in an eye, a footprint that says, I was here, and for a while I had the sky.